Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Dr. Mark Hepikoski. Dr. Hepikoski is Chief Scientist for Physiology and Comfort at Thermal Analytics. He joined the team in January of 2002 as a software engineer and has amassed over 2 decades of experience at TAI in various research, development, and administrative roles, including those of Director of Advanced Research, Chief Scientist, Chief Technology Officer, and Product Management Director. He has personally developed a large number and a wide variety of thermal modeling algorithms for the Tytherm family of commercial heat transfer simulation CAE tools. Dr. Hepikoski received his BS in Engineering Science and Mechanics from Virginia Tech. He also holds MS and PhD degrees in Mechanical Engineering and Engineering Mechanics from Michigan Technological University. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We're also recording this webinar and we'll be sending you the link following this presentation. And with that, Mark, if you're ready, you may begin.
Thanks, Chris. I just wanted to give a disclaimer that I'm a little bit under the weather right now, so hopefully I don't end up in a big coughing fit. So anyway, yeah, I'm gonna move on. So yeah, we're gonna look at some advances that Thermal Analytics has done in making clothing or simulation, clothing simulation much more straightforward. For those of you that are not familiar with Thermal Analytics, we're a small company. We're still a small company, and we're located in a place called the Upper Peninsula of Michigan, something we call the Copper Country. So we started in 1996, and we started becoming an employee-owned company in 2002. We were a break-off actually from the university research group there. Then we started establishing offices, other offices in America, and as well as in Europe, and most recently in Tokyo. And then 2023, we became a fully employee-owned company. So that means that there are no external shareholders. We're all stakeholders in this company. Again, if you're not familiar with our operations, we develop software. We do participate and help guide people in developing human subject tests, but our primary area of interest is developing engineering software tools. And so the most important one, I think, is what we call Tytherm. And then there's a defense-oriented one called Muses. It's essentially Tytherm with the capability to be able to predict what EOIR cameras might be able to see. And then Cotherm, which is a process automation tool. So within Tytherm, you can solve any heat transfer problem, and we provide this extension which automates the simulation of humans, and that's what I'm going to be focusing on today. So I'm going to jump right into it. First, start with the motivation. Why do we care about this? Clothing isn't just for like this webinar is not just for people that are in the clothing design industry. In fact, it's much more for people that really want to be able to accurately predict heat transfer across the human body. If my clothing's wrong, I'm going to get wrong thermal sensations, and the clothing can be wrong for a number of reasons. It can be either bad data from a mannequin. It can be data from a database that has an error in it, or because often engineers use these kind of tools, they might misinterpret what some of these clothing properties are. So anyway, yeah, if you get wrong heat transfer, you get wrong temperatures. If you get wrong temperatures, you get wrong sensation. If you get wrong thermal sensation, you get wrong comfort. But obviously, we also care about clothing for human effectiveness, whether we're talking about soldier clothing, soldier uniforms, or personal protective equipment. And then also, as I mentioned before, if we're simulating what somebody might look like in an infrared, with an infrared camera. For those of you that are not familiar with clothing properties, it's really best to kind of start with, well, how are they measured? And you'll see a couple different devices out there. One is called a sweating hot plate, and the other is it's called a sweating thermal mannequin. At first glance, you might say, well, I need some clothing properties. I just need some R values. I think that this sweating hot plate will do just fine for me. It's relatively cheap and easy to obtain. I can kind of run it on my desk. And it gives me an R value. And if you've got a sweating module, it will also give you an evaporative resistance. So a thermal and an evaporative resistance. But if you'll notice the subscript on the R, it's an F, which stands for fabric. And what the con with this is that the resistance of the air gap is not measured. And I've seen some researchers report that, often with a clothing ensemble, I think it's less than 10% of the thermal resistance is due to the fabric. The rest is the trapped air. And the only way to measure that trapped air is by, having the clothing worn on a device that is in the same form as the human body. So mannequin measurements mannequins have been around for over a century. I think the late Eugene Whistler said that he found a paper. It was a French scientific paper about somebody had developed a wooden mannequin in order to be able to measure clothing heat transfer. And then those, of course, been developed over the years. I think the Thermetrics mannequins that we're seeing right there are really considered the state of the art. And but basically, it's a real simple process. You take your mannequin, put it in a chamber of known air temperature. You set your mannequin so it's got a target temperature, 35 or 34, and then the surface area, and then in order for it to maintain those temperatures with the clothing ensemble that it's wearing, there's an amount of heat that has to be generated that's reported by the software. And so we have all of the knowns on the right-hand side, so we can then calculate something called a total thermal resistance. So what we find in the literature is a lot of there are databases in literature prior to actually, or right when we started doing thermal modeling, but they were all these whole body values. And there's many different terms. There's total thermal resistance and intrinsic clothing resistance and air ambient air resistance, which I'll get to in a second here. But when you think about really what's going on here, the whole body clothing resistances that are measured by a mannequin, they can really only be applied to a simplified human representation of the body. So in real life, I'm kind of showing, if we were going to be more physically rigorous, we've got a human being and they've got thermal resistance, which represent the R values. And you can see that the R values of the clothing, it's changing based on just the type of garment. Not only that, but also the air gap is trapped. You have some body segments that are completely exposed to the environment. Well, all of that information, all that heat transfer is going into this R value. So you can only really use it if you've got a simplified representation of the human body, like something like the 2-node model. It just says, okay, the human is a cylinder, and we're going to model all the physiology with that. But again, the reality is different. And so these databases that we find in the literature, we often have to perform this kind of localization process, which you can find described in the literature. But those really won't give you like a first order approximation, and you really need to measure these R values at a local for each individual body segment, body zone. And once we have those, then we can apply them to what we call a segmental thermal regulation model. So just like I showed before, where, okay, we're going to say the human is a single cylinder. Here we're saying the human is multiple cylinders and even a sphere for the head. So we've got like higher resolution across the body, as well as through, if you look at this cross section of the thigh, you can see how like the the body then is further subdivided in terms of volumes, which then are reduced to nodes. And so I might have 100,000 locations throughout the body where I'm solving the bio heat transfer equations, so I can get at those local skin temperatures and ultimately calculate mean skin temperature, core temperature, and thermoregulatory responses. For people that are not familiar, like again, just traditional mechanical engineers, they're not going to be familiar with some of this terminology. The basic theory is really quite simple, like I showed before, but it's very important to understand some of the words that are the jargon that's used in this textile world. So here's kind of a picture on the right-hand side, part of a cylinder. You can see there's something called an air layer. There's the enclosed air layer, and then there's the clothing, and then there's the body, and there's something called the total resistance. There's the air layer resistance, and then the intrinsic clothing resistance. What's confusing, I think, or potentially unintuitive to an engineer is when they hear, if you're not in this world, in the textile world, you hear air layer, because often it's not specified the way it is here, surface and enclosed. It'll just say air layer. That actually means, we would think, oh, that means the air gap in the clothing. It actually means, no, it's the air outside of beyond the clothing, between the clothing and the environment. So it's really important when you're doing thermal simulation, we need something called the intrinsic clothing resistance. That means when we take our measurements, we measure the total thermal resistance, we have to subtract off the air layer or the surface air layer, and then that's going to give us the intrinsic clothing property. I think there's so many different subscripts and terms in this field of science. But I think when you're, from a practical perspective, if all you're interested in doing is ending up with these RCL values, really this is all you. These are the most important terms to understand. R means resistance, RE means evaporative resistance, and I've got air or ambient, I've got T for total, and then I've got CL for intrinsic. And then there's also something called a clothing area factor, which is dimensionless. It just represents the increase in surface area, which is going to impact heat transfer that is associated with this ensemble. And of course, units of Clo. I personally, everybody's got their own preferences. I only use Clo to represent the whole body values, and I like to use SI units when we're talking about local clothing properties. So it's really quite, we're going to run the same kind of an ASTM test or ISO standard test. You get the mannequin so that it reaches a steady state, and then you basically perform that same calculation with all of these knowns. You know the local skin temperature, you know the operative temperature, you know the surface area, you know the heat, so then you can back out what the R value is. And you run a nude test, you run a clothed test, and then once you understand, get an estimate of the clothing area augmentation factor, then you can calculate those intrinsic clothing properties. So fortunately, we're seeing, I was really excited about this when I heard that it was coming out, was these high resolution data sets for modeling, really that are perfect for modeling humans. And so these, there's one, a Western ensemble data set, there's a non-Western ensemble, there's, I think there's a medical clothing one, and then we're also seeing, different kind of personal protective ensembles. And there's a lot of data that's contained in these data sets, because if you think about it, even just for one ensemble, you can do many measurements. For example, the R values, the local R values that you get are going to be a function of posture or pose. They're going to be a function of the air velocity. And so just for one ensemble, you might have like 6 different variations. So quite a bit of data there. And so if you think about this problem, the process of bringing in all that data into a thermal simulation tool, it requires quite a bit of manual labor. And you got to have a little bit of an understanding about what it is that you're doing. And so it's again, because it's a different field of science than most mechanical engineers, it's really easy to make mistakes and come to the wrong conclusions, make incorrect assumptions. So basically, it's really great. We have these databases. Now we got to get this into the software. Usually in the past, we'd always do that with, this kind of really huge Excel spreadsheet. But we realized that a much better way is just to automate the process. It's essentially the same process for every single ensemble. So that's why we developed this, this thing called the Clothing Manager tool. The idea is just to provide a way to easily browse and select clothing ensembles, click on them, and then apply them, and basically in a second have all of that high resolution data ready. So it's going to automatically do all of these calculations. So that assumes that these high resolution data sets have total thermal resistance and resistance of the air layer and clothing area factor, and then also thermal and evaporative resistances. So kind of just describing the what's actually happening behind the scenes. We also wanted to make this very user friendly, so that you might have a data set that because there's many different types of mannequins out there, different zone configurations, and then there's many different models. Your models, basically you can do your own segmentation and in Tytherm, where you can group any elements that you want into body parts. So the idea is if I've selected an ensemble, it's done with a 32, that's measured with a 32 zone mannequin, but I've got a 20 compartment mannequin. I don't have to go through the trouble of kind of readjusting to get a one-to-one mapping. I can do that, but maybe the 20 zone resolution is good enough, and that's where that averaging comes into play. So some of the built-in ensembles that we currently support is the Western Clothing Ensemble, Samalcombe et al., published in 2021. A lot of organizations involved in that study, and then very importantly, they have male and female clothing. And then Kalev Kuklane recently published, or he's been publishing some papers that describe in the same manner the firefighter turnout gear, different ensembles. And then, of course, with this clothing manager tool, you can also bring in your own custom ensembles. So I'm just going to give a brief overview of what it looks like. So first, there's the ensemble picker. There's some filtering. I can filter by insulation, whole body insulation. I can also filter by, I'm looking for female clothing, or I'm looking for PPE garments. And then you've got your ensemble selection. The whole body clothing properties, again, described in terms of CLO, and then vapor permeation efficiency, which really combines the thermal resistance and the evaporative resistance into a single dimensionless number, and then the whole body area factor. And then because we're just looking at a single R value that represents the entire stack up, it's nice to kind of get a little bit more clarity on the individual garments that make up the ensemble. Of course, we get more detailed images in these databases. There's quite a number of photos, and then of course the name of the currently selected ensemble, and then if there is a reference or a DOI in the literature where you can click on just to get what the actual paper or reference is. One of the things I'm excited is that we're also adding an option to run something called Berkeley set points. So for those people that are interested in running a thermal sensation, being able to predict thermal sensation and comfort, well, you need to generate a reference state. And the reference state is a function of your clothing and your activity. And for this, basically, you just provide the path to the executable. Obviously, you need the path to the TDF in order to, that's the Tytherm file type in order to import the clothing. And then if you select the option to run Berkeley set points, you also need to specify the activity level and the activity type. And if there's some kind of error, we provide user-friendly progress in the error messages. But that's all there is to it. Click apply. There's also some additional settings that I'm going to talk about in a second here. And then there's also kind of the equivalent of an about. When I click on the settings, I can look at, for example, the custom tab. I can specify those Excel files or CSV files that describe the ensemble, and then it'll be saved to the database, and then the human thermal clothing manager will always know, will always have that available for selection. There's a mapping. I mentioned the compartment map averaging, which is kind of just that coarse that mapping of measurements to model body segments. But we always recommend that's going to work every single time. And then we also recommend this high resolution mapping, which should work 99% of the time. Basically, it's looking for keywords in the mannequin data and in the model, in the part map in the model that are related. So there might be, if it sees the word upper or mid or lower or back or front, then it'll automatically, because it knows the part name and it knows the compartment that it belongs to, then it's able to do that high resolution mapping. And I think for the most part, you'd be able to get a one-to-one correspondence between mannequin and model. But if you really wanted to make sure that that's very important to you, then you'd want to map using exact part names. All right, so with that, I'm going to do a real quick demonstration of the value of this tool in the context of Tytherm, the human thermal model. What I'm going to do is it's kind of in the context of an automobile scenario, but it's a very simple. It's what we call a cold transient heat up. If you're not familiar with that, that's just like on a very cold winter day, you go out to your car and then you turn on the car and then there's a transient heat up, just like you think. For this, I just took the 50th percentile male, the standard male model that comes with the software installation, which is described here. I chose an ensemble that had some higher clo value, 0.88, seemed kind of reasonable, maybe a bit light for real cold winter, but good enough for this demonstration. Again, this came from the Smallcomb et al. Database, the Western database. Before you run any kind of simulation or even any test with human subjects, and you typically have them stand out in the wind tunnel for about 5 minutes so that they get cold and uncomfortable when you're doing a transient heat up. So we want to simulate the same thing. So you think of the person, they're outside in the parking lot for about 5 minutes, and then they enter the vehicle. So then we run that simulation. We see what we would expect, a very cold thermal sensation state. And then we can see kind of the transient heat up until it kind of reaches a steady state. We're looking at equivalent homogeneous temperature or equivalent temperature in blue. That's kind of like the temperature that you'd feel. And then there's the mean radiant temperature, because as the air is moving inside the cabin, it's slowly warming up the surfaces in the cabin, or perhaps cold windows. And then we also have the mean convective temperature, and so that's going to be the air temperature, which is going to be it's going to move it's going to move to a higher temperature. And so there's going to be this lag in the mean radiant temperature. So it's kind of a typical, something that seems should be somewhat intuitive. And so it's a 30-minute scenario. Because we're running a thermal physiology model, we're calculating all these local skin temperatures, but we can look at them in terms of the mean skin temperature, the hypothalamus temperature. These are the temperatures that are used to calculate how much sweating and how much shivering and how much vasodilation and vasoconstriction need to be applied at every single moment in the simulation. But you see what you'd expect, right? The skin temperature drops, kind of reaches a minimum, and then there's this rise in skin temperature. And once the skin temperature achieves a reasonable, closer to a neutral temperature, the derivative of the skin temperature, the time rate change of the skin temperature, that has a huge impact on how hot or how cold I feel. One thing I'll point out is that there's not much change in core temperature, and we wouldn't really expect to see a huge one. Here's the results. So we can look at all that physiology, all these boundary conditions, they result in an overall thermal sensation, and then which is in blue, and then the overall thermal comfort, which is kind of that yellow color. And we can see that then there's the pink background transitions to a green background to show the time to comfort. So we can right away identify that, okay, for the first 13 minutes, this individual is uncomfortable, and we can see the minimum comfort that was reached and the average thermal sensation. And then we can look at the time to actual comfort, which we would say is 14 minutes, and the person's comfortable over that entire time period. And they kind of reach this 0.9, which is effectively 1 on the scale. So they're comfortable. And then the average thermal sensation that was experienced is a neutral thermal sensation. So I reran the exact same model. All I did is I took the female, 50th percentile female, and I dropped her into the exact same simulation, exact same clothing. But looking at some of these physiologic results, it's interesting because we're seeing some shivering, a small amount of shivering. And even though she's wearing the same clothing, doing the same activity. The mean skin temperature, similar trends as the male, but we're seeing on the hypothalamus or core temperature, more nuanced. It's not just a flat line like it was with the male. That's because of that shivering that the female is experiencing. When we look at, so we're seeing a very similar overall thermal sensation, overall thermal comfort. For the female, it takes her about a minute longer in order, the cabin has to get a little bit warmer, and she has to get a little bit warmer for her to cross over into the comfort region. She achieves essentially the same maximum comfort that the male did, but the average thermal sensation, rather than being neutral, is kind of between neutral and slightly cool. So she's feeling a little bit cooler. Now, the last variant I wanted to try was just choosing a different ensemble from the database. For this one, we took Ensemble 48. Something that's kind of more female. She's wearing a dress or a skirt and a cardigan. What was interesting here is that kind of what we'd expect is that so the time to comfort is, there's less also thermal. So not only is there less coverage of the clothing, there's also less whole body thermal insulation. And so it's going to take her longer in order to reach comfort. And you can kind of see it's kind of just really riding here between just uncomfortable and comfortable. And she doesn't really break free into being fully comfortable until about 23 minutes into the simulation. So we can say, time to it's somewhere between 20 to 30, but she only reaches a maximum comfort of 0.7, which corresponds to something closer to just comfortable. And her average thermal sensation now is much cooler than the previous male and the female wearing the same clothing. This kind of summarizes the results. So we looked at the male model, and the time to comfort was 14 minutes, maximum comfort was 0.9, average sensation was neutral. For the female, wearing the same clothing, took a little bit longer to reach comfort. Max comfort was about the same as the male. Average thermal sensation was slightly cooler. And then finally, the female wearing typical female clothing or more representative female clothing, it took her a lot longer to get comfortable in that same environment. And her average thermal sensation was slightly cool. Excuse me. So to summarize, we talked about some of the science, the basic science behind deriving clothing properties and fabric properties, and also hopefully helping engineers that see databases in the literature and they see SI units associated with that, and they see things like total thermal resistance, to beware that you really need to understand what these values mean before just taking them and importing them into a model. So, but more importantly, you need to have high resolution modeling because of the clothing, because the sensation and comfort, they're inherently local phenomena. And if you want accurate sensation and comfort, you need to get accurate skin temperatures. And in order to get accurate skin temperatures, you have to have accurate heat transfer. So I found myself, as we just released this tool, I think it was last Friday, the first release, and it was really fun to use. I was able to do, like, for example, this really quick turnaround study that I just demonstrated here. And it provides a way to look at some aspects of individual variability. And I could have done a lot more. In fact, you could do a whole DOE and then in your thermal simulation, in your predictions, instead of just saying, okay, here's a single curve that represents what you should expect in a real test scenario. No, you could calculate all of those curves and calculate average and standard deviation with error bars. So anyway, but hopefully I got the point across that, in these example models, that you can see these differences between male and female, that some of it has to do with anthropometry and physiology, and then, but a lot more of it has to do with the different clothing ensembles that females typically wear. So that concludes my presentation.
All right, thank you, Mark. We can go ahead and open it up for some questions here. The first one, does the human thermal clothing manager consider the thermal capacity of clothing?
Okay, yeah, that's a great question. So the Titherm considers the thermal capacity. You specify the clothing layer parametrically in terms of thickness, a density, and a specific heat. And that combined with the area kind of gives you your MCP. And with most typical ensembles, light ensembles, you don't really need to consider thermal capacitance. You're not going to get much of a change in your results. However, if you are running with like personal protective equipment, like firefighter turnout gear, we've been doing some research recently, and we're going to be presenting this at the European Conference for Protective Clothing, where thermal capacitance is absolutely critical to capture correctly. In fact, it's even more important than some of these other properties. So yes, you can model thermal capacity in Titherm. to whatever detail that you'd like. But currently, the clothing manager, these high resolution data sets don't currently report things like specific heat or density, but they do often provide the mass.
Okay, thank you. Can you provide guidance on how often comfort set points should be recomputed?
Yeah, so as I mentioned, anytime the clothing coverage changes or the clothing insulation changes or anything thermally about the clothing, even the surface condition of the clothing, if that changes, that impacts the heat transfer. Anytime the heat transfer is impacted, you have to regenerate your Berkeley set points. Also, yeah, anytime the activity level or the activity type determines the distribution of heat across the body and the muscles of the body. And then there's also, but if I change gender, so I go from the male to the female, I'm going to end up with different local skin temperatures in my reference state, so I have to generate my Berkeley set points. And then if I change the anthropometry, if I scale away from the 50th percentile height and or weight, or change the body fat content, anything that impacts temperatures in the human system, anytime I make a change there, I have to regenerate my Berkeley set points. And so hopefully this new button, where we make it easy for the person, for the user, we provide that capability. It does take, to run the Berkeley set points, it might take, 20 to 30 seconds. And so there's a little bit of a time hit there.
All right, thank you. Will the mannequin parameters be manageable in Cotherm to precondition the occupant prior to any transient runs?
Will the mannequin, can you repeat one more time? Sorry.
Yeah, no worries. Will the mannequin parameters be manageable in Cotherm to precondition the occupant prior to any transient runs?
I think I don't actually use Cotherm that often, but there is, because it's a process management tool, and so I think the mannequin properties can be made available depending on the Cotherm process that you develop. And unfortunately, I think that I don't 100% sure, but anyway, I maybe we can follow up with that individual.
Yeah, sure. All right, this is and we can, and again, let me know if this is one of the one you want to follow up with later. But how is this clothing manager different from Tytherm? Means even in Tytherm, we can model the clothing into layers and can provide the resistance for each layer to capture the heat transfer between ambient and the mannequin. So how is the clothing manager more effective?
Yeah, no, that's a great question. So the clothing manager, all it's doing is setting up a Tytherm model. So yeah, you can do everything just within Tytherm. You don't need the clothing manager. You can create the same ensembles. And that's used to be what we would do. We'd create an Excel file, we'd do all this processing, and then create one of those BC import files. We import clothing properties and assign them into the model. So yeah, but I think like one of the things that's in Tytherm, there's that traditional, there's like a database. It actually comes from Liz McCullough from Kansas State University. And that's where you kind of dress the mannequin as you would a Barbie doll or a Ken doll, where you do it in terms of garments. Each one of those garments was measured on a thermal mannequin and expressed as a whole body value. And so what we did is we went through that data set and we reduced, we kind of create localized versions of those, but that's really only a first order approximation when it comes to accuracy, because if we just take, for example, trousers, Well, there's many zones that the trousers are insulating, and you're going to get different R values, depending on if you're talking about the calf or the thigh. And so really that approach is somewhat antiquated now that we have these high resolution data sets. However, if you're designing clothing, if you're an actual clothing designer, textile designer, then those people are often looking at clothing systems, or those scientists are looking at clothing systems, and so they might be modeling things like Gore-Tex and modeling the moisture, and they're really focusing that they'll have the clothing ensemble system comprised of 8 or 9 layers, and that it's all application specific. So if you just want to have you want to run a human model, and you want to say, you know what, I don't really care that much about the clothing. I just want to have winter clothing and summer clothing, but I do care that they're accurate. You should really just use the clothing manager tool. It just makes it that much easier.
All right, thank you. Next question. For the thermal and evaporative resistance parameters in Titherm, which units should we key in?
Yeah, in Titherm, it's the SI unit, so it's in the material property, it'll be meters squared Kelvin. Oh no, sorry. Yeah. I'm a little bit groggy. I really apologize for this sickness, but it's meters squared Kelvin per watt, and then there's meters squared kilopascal per watt. Those are the units, and they're specified in the user interface. It'll clearly mark what the units are for R and RE.
All right, thank you. You showed the comparison of model results and expected outcomes for different settings. How well does it match with human data? And then parentheses, bias and variation.
Yeah, so like I said, this was just a demonstration of models, but we've done tons of validations. Usually what we do in those validations is we use these sensor mannequins or HVAC mannequins, and those basically have like 180 different sensors. We convert those to boundary conditions for use in the model. So basically we take the measurements, in this example, like we're a transient heat up, and we've got human subjects in those vehicles measuring skin temperature, they're reporting their sensation, their comfort, their most uncomfortable body segments, and that sort of thing. And then we've published quite a number of those data sets, and what you see is there's really quite good agreement between what Titherm predicts and the human subject measurements.
All right, thank you. Hi, how should I calculate FCL if I want to put some data into the program?
Yeah, that's okay. So I think I had it in. It's not so okay. If I, because often what you get is a whole body FCL, and the way that they measure whole body FCLs is they'll take. I mean, in the past they would take pictures, but what we've done is we've used we'll do a body scan. So you do a body scan of the person wearing the ensemble, and then a body scan of the nude ensemble, and then we'll use data analytics software to calculate. Essentially what you're doing is you're calculating the explicit air gaps, but then you're able to calculate the change in surface area from the one scan to the other. So then if that's all you have in the literature, because somebody said, okay, here's your whole body clothing area factor, well, then you do need to know your surface area coverage. Like how much does, are we talking about, I don't know, shorts and a t-shirt? Are we talking about firefighter turnout gear? And so we need to know how much of the surface, how much of the body is covered in the clothing. And basically what we're doing is we're just reducing or increasing or readjusting the FCL so that it can be applied those body segments that are covered. But keep in mind that in a perfect world, you'd want to actually measure the local FCL, and that's really getting back to what I said before. You'd really want to do a body scan, subdivide your human, and for the upper right arm, get the actual real FCL, which is, it's just the surface area of the clothed mannequin divided by the surface area of the nude mannequin body segment. And that's the most rigorous way. And FCLs are important not only for in thermal simulation when you're modeling the clothing parametrically like you do in Tytherm, but also in the derivation of these clothing properties. As you can see, the FCL appears in the derivation of the RCL and the RECL. Hopefully I answered the question.
All right, thank you. Temperature ratings for gloves and boots is difficult. Is it possible to model thermal comfort for just hands and feet if the RCT, RET is provided for the ensemble on the rest of the body?
Yeah, that's a good question. So you said to calculate, again, I'm a little bit groggy. It was for calculating sensation and comfort. Is that correct?
Is it possible to model thermal comfort for just hands and feet?
No. Yeah. And so that's what the Berkeley Comfort Model provides. It'll give you thermal sensation and thermal comfort resolved at about 20 different body segments. And so I can actually look at the hands and it'll report the thermal sensation and thermal comfort of the hands separate from the thermal sensation and thermal comfort of the feet. And I think like the big trick is that how those local sensations influence what my whole body comfort is, because at the end of the day, that's what you care about. Is if I'm designing a product, is this making the person more comfortable? So obviously I care about the thermal sensation and comfort of the hands and the feet, but I also care, probably more importantly, that when you ask the person wearing the product, hey, are you comfortable? And they say, yeah, I'm comfortable, or I'm not comfortable, or I prefer this product over another product. The model should be able to tease out those differences from product to product.
Okay, got time for one more question. Why is it important to model the air layer resistance?
Yeah, that's great. Okay, so in that image, hopefully it was right here. Yeah, okay. So hopefully this image makes sense. The thing is that in a thermal simulation, like if you think about, I've got a human body that I'm trying to simulate, and maybe I'm going to use CFD, computational fluid dynamics, to model my air. So here I'm modeling the physics of this air layer, because this air layer right here represents the measured ambient air resistance, or ambient resistance that was measured in the chamber. So if you don't subtract off this RA, what you're doing is you're saying the human that I'm simulating that's outside and there's all this fluid flow, cold air flowing over them, they're actually sitting inside of a chamber. Like they're wearing the clothing, plus they're sitting inside the chamber, and the chamber somehow is magically there in the scene, and then you're modeling additional fluid flow. So you're kind of double counting. So the point is that we don't want this air layer that's measured from the chamber. We're going to simulate in Tytherm the air, this air resistance. I mean, air resistance is just right. The reciprocal of that is the convection coefficient. It's really convection coefficient plus the radiation. You can think of it as linearized radiation heat transfer coefficient. But the point is, if we just disregard radiation here, this is just 1 over the convection coefficient. Well, we're going to be supplying what the convection coefficient is in Tytherm. We don't want this convection coefficient. This is the convection coefficient for still air in a chamber. We're going to be modeling high-speed air or higher velocity air.
All right. Well, thank you. That'll do it for questions. If we did not get to your question, we will be following up with you directly via email later today. That will complete today's webinar. We appreciate you all attending. Everyone will be receiving a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Again, thank you, Mark. Thank you everyone for attending, and everyone have a nice day.
Thank you.